So now that we've talked about momentum, kind of the natural follow-up question or kind of following point is how does that momentum change? And that's where we look at this idea known as impulse. So forces can create changes in momentum. And this is because of Newton's second law. So if we start with net force equals mass times acceleration, we can rewrite that as mass times change in velocity over change in time, which we can rewrite as mass times change in velocity over change in time, which can equal mass times velocity minus initial velocity over change in time, which is equal to mass times velocity minus mass times velocity initial over change in time, which in other words can just be the final momentum minus the initial momentum over the change in time, or just delta P over delta T. So from Newton's second law, knowing that acceleration is a change in velocity over change in time, we can rewrite this whole expression as net force equals delta P divided by delta T. And we can also rewrite this into the impulse-momentum relationship, which is that change in P is equal to net force times change in T. And that's because we've got the momentum piece on the left side here, which means that this right side is our impulse piece. So this quantity on the right is known as impulse. It's mathematically equal to a change in momentum, but it is technically a different thing. So impulse is defined as a net force applied for a certain period of time. So if you push on a box with 10 newtons of force for 5 seconds, that impulse is 50, 10 times 5, 10 newtons times 5 seconds. So in other words, yeah, that's what impulse is. There's no standard variable. So there's no variable for impulse. We just write force times time. But the units are Newton seconds. They are Newton seconds, which is also equal to a kilogram meter per second. So technically the units of impulse are Newton seconds. The units of change in momentum are kilogram meters per second. The two are equal, but if you're going to talk about the impulse, it's better to say it has 50 Newton seconds rather than 50 kilogram meters per second. It's not wrong to use the momentum units and impulse units on each other, but it is not standard, what we'd say. If we have a force versus time graph, so time and force, something like this, then the area here is impulse. Impulse. And that's just a thing to note that we can find the impulse from a force versus time graph, or we can estimate it, right? We could estimate a triangle, a rectangle, and then a trapezoid to estimate the area of this. And that would tell us what the impulse is. It would also in turn tell us what the change momentum of whatever this is describing is. So here's an example. Suppose that a 150-gram baseball experiences an average force of 480 newtons in a direction opposite the initial 32 meters per second speed of the baseball over a time interval of 0.017 seconds. This is a fancy way of saying the baseball is hit. What's the final velocity of the baseball after the collision? Well, we know that the change in momentum will have to equal to the net force times the change in time. And the net force, or the average force, was 480 newtons, so that will equal to 480 newtons times 0.017 seconds. Change in momentum is also equal to final momentum minus initial momentum, which will equal mass times the final velocity minus the initial velocity. So we know the initial velocity was 32 in one direction, and the final velocity is going to be in the opposite direction. So I'm going to say it was initially going to the left and make this initial velocity negative. That will also let me make the force in the positive direction. This is where it's going to get tricky. So we know that the force is to the right. We know that the initial velocity is to the left and the final velocity is to the right. So force and final velocity should be positive. Initial velocity I'm going to need to make negative. This is where drawing diagrams for this unit is going to be really important. So this is also equal to 0.150 kilograms times the final velocity, which is unknown, minus the negative 32 meters per second initial velocity. So I just plugged all that in so you can see where we're going. I'm going to go back to symbols for actually working this problem out. And we're going to have m times v minus v naught. This is change in momentum, and that will equal the impulse applied, F delta t. We want to solve for v final, so we're going to get v minus v naught is equal to net force delta t over m. So we're going to get v is equal to v naught plus net force delta t over m, which is negative 32 meters per second times, or plus 480 newtons times delta t, which is 0.017 seconds, divided by kilograms of baseball, so 0.150 kilograms. Newton is a kilogram meter per second squared, so if you do kilograms meters per second squared, you multiply by seconds, the seconds cancel, divide by kilograms, you're left with just meters per second, so our units will work out. I'm not sure what this value is, but it's going to be something in the ballpark of 0.002 times 480 will be basically 1,000 divided by 100, so that'll be about 10 divided by 0.15 will be about 3. Two-thirds, so 0.66, 3/2. I'm blanking on doing this in my head, but you can plug it into a calculator, see the gist. If you want me to double check your work, ask me in class. But that's the idea here. Behind this, the key part is right in here and this initial setup, and remembering that we've got to draw a good diagram.